Welcome, everyone. This is the start of week 11, thermal energy and heat. I'm at testing today, the 31st. So this is the best I'm going to be able to do for you guys. So let's get started. This is an Edpuzzle. So this will count as week 11, assignment 1, 15 points. Happy birthday, Brianna. Her birthday 4-2, Nevaeh, A 4-2, Autumn 4-6, and Rojaya 4-1. All right. Happy birthday for this beginning of the week of April. Right. So week 11. Okay. So there are some notes for you. This is thermal energy. What we're going to be learning is about temperature and heat, temperature scales, thermal equilibrium, phase changes, and phase diagrams. Our intent here is to understand and predict heat transfer, which way it goes. Does it go from cold to hot to cold, cooling? This is important in terms of, how to insulate your house, things like that, how to keep warm or keep cool, especially in the changing of the climate because of global warming. Last week we had record heat wave in the beginning of spring in Arizona, 99 degrees. And so it's arriving earlier. And that seems to be what global warming is doing. Right. So heat is very important in our daily life. As I said, cooking, heating, the materials we use to protect ourselves, the clothing we wear. We will learn this week mostly from Edpuzzle. Okay. Probably won't be doing any Phet Labs unless we get a chance to put some in there. I'm not going to be doing bonus this week. So anything I assign you is considered an assignment with points. So let's watch this this bunny.
It's not having access to 1 million industrial grade products that's so amazing. It's the feeling of knowing you'll find the one you need.
There we go. So it's getting close to Easter time in 3 weeks, right? Hot iron. Oh, melting occurring. I'd never do that. I would eat the top of the bunny off. Waste of good chocolate. So which way is heat flowing? From the bunny to the iron, or from the iron to the bunny? Heatland strikes again. don't know what it reminds you of, but it really reminds me of having candy bar in my pocket. I'm going to somewhere and I'm going to save it for later, and then I forget it's there and it melts in my pocket. Right. So what we're talking about today is the kinetic theory of matter. Kinetic means motion. So we've been talking about kinetic and potential energy. So kinetic theory of matter states that particles make up matter, and they're constantly in motion. So even, we don't see them, so you can think about it in the states of matter. So the states of matter, solid, liquid, and gases. So solids, the material vibrates back and forth in place, just kind of shaking there. Liquids, the particles move past each other, so they're more freely to move past. They are in a higher vibrational state. And then the gases are far apart and moving around at high speed. So gases have a lot more kinetic energy than solids do, right? So things that we take a look at. So if you look at this diagram here, you can see the shaking. The temperature here is colder, right? If you can see this, don't know if you can. All right, so here's the temperature here, right? So let's say this is a solid. All right, here, things are moving past each other, higher temperature. This was a liquid. And then here is the highest temperature. And look at the vibrations, the gas. So solid, liquid, and gas. So a solid, let's say these are the same things. Solid ice, liquid water, gaseous water. So things are moving much more quickly as we add heat to them. So let's look at this labels. Using 1, 2, and 3, which has the most kinetic energy and which has the least kinetic energy, right? So if we're looking at this, if I'm going to label them, which has using 1 as the most and 3 as the least. So this would be number 1, having the most kinetic energy. You can tell that again, they're further apart. And if we were to see a visualization that these are bouncing against the wall, bouncing against each other, this has a little less energy. These molecules are sliding past each other. And these solid has the least amount of kinetic energy, and they're just vibrating back and forth, and they keep their shape, right? This fills the container, or I should say fills the shape of the container, but it doesn't. But here, when we get it to be gaseous state, it fills the whole container, and it really, if I were to open this, these would escape. Right, energy of motion refers to, right, which of these energy of motion is it? Electrical energy, kinetic energy, static energy, gravitational energy. So let's go back there. This was kinetic energy. Kinetic means motion, right? What is the kinetic theory of matter? Because particles move at various speeds, each particle has its own kinetic energy. So that's why we do an average. So if you take the temperature of something, you're taking an average of the kinetic energy in the materials. So some may be warmer than others. You think about something that's a solid, the outsides are closer to the room temperature. Insides might be cooler depending on what's going on. So when we take a temperature, we're taking an average temperature. That means the middle between the lowest point of the material and the highest point. So low and high of the material. So we put a thermometer in there, right, to measure the temperature. And we get an average, so somewhere in between the low and the high. Right, so temperature is it a measure of average kinetic energy of the molecules, the difference between the amount of heat between two substances, the total kinetic energy due to the motion or the thermal energy due to the interaction between molecules. And again, what we said just before, this is the average kinetic energy, right? Average. So, and remember, like when you're adding, let's say you have grades and you want to average the grades. Let's say you had 100% on one assignment, and then 80% on the second assignment. We add those together, we get 180, right? And then when we divide by 2, because there are 2 assignments, we get 90. That's what we call averaging, right? So how your grades are looked at. So what's the average kinetic energy of the temperature of solid ice? Right? You should know for the Fahrenheit, maybe not so much Celsius. Celsius is easier in science to use. So the average is 32, and the reason that they have 32 is because the guy that made the thermometers, at one time there were 23 different thermometers. And the guy that named Fahrenheit, he was a good thermometer maker. He decided 32 is where I'm going to put this at, and everybody started using it. That was where freezing of water is, 32. Later on, scientists said, hey, it would be nice if we can set this. Why don't we just set it at 0? And they called it 0 degrees Celsius. And that's how we use that. Instead of calling it 32, they called it 0. But we use Fahrenheit because right now, it's 50 degrees. So 50 degrees Fahrenheit is about, I'll have to check that out. It's lower. It's probably only 15 degrees Celsius. All right, the average kinetic energy. Okay, putting a thermometer in here. Okay, checking the temperature, right? And again, closer to the bottom will be hotter, or the top would be cooler. So we take an average. So what is the average temperature of boiling water? Okay, if you said 212 degrees, you're correct. Celsius is 100. Again, the Celsius, remember, freezing was 0 and boiling is 100. Much easier for science to remember than to use all the 23 different thermometers that came before it. So there are 3 different types where science uses Celsius and Kelvin. Celsius starts at 0 for freezing and 100 for boiling, but Kelvin is commonly used by physicists. This unit is called Kelvin instead of degrees. Water freezes at 273 degrees Kelvin and boils at 373. So basically what you're doing is adding 273, right? For freezing plus 100, the Celsius 100, that gives you the 373. Okay, so 0 degrees K is when or Kelvin is when we have no movement in molecule at all. Okay, matter stops moving. Remember, I told you that solids vibrate. Here, if we ever get to that point, we got very close to 0 degrees Kelvin, but here would be where no movement at all, and that's what they figure, right? So example, if you pour hot coffee into a pot or into a mug, the amount of coffee will be different, but the temperature will be the same because of the average kinetic energy. So again, got a hot pot of coffee, and let's say the interesting part is if you are a Starbucks fan, I used to work at a Starbucks, 200 degrees Fahrenheit is where they got their coffee. They said that's the temperature we need to brew the water, get the water hot enough to make coffee. And they were really strict about that. They had a special container that would get to that temperature they thought it would, if over that temperature, coffee didn't taste very good. So you've got a pot that's 200 degrees and then 200 degrees for the cup of coffee, right? That was their best. But again, the bigger container, the temperatures were the same, right? So what happens when the kinetic energy of particles increases? Kinetic energy of particles, what happens to the, all right? What happens when kinetic energy of particles increases? The temperature does what? The temperature does what? Okay. So does it increase, decrease, or stay the same? So if we're, think about it, when you rub your hands together, you are increasing the kinetic energy. Does your hand feel warmer or colder when you rub your hands together? All right. So we're talking about the temperature increasing, right? Temperature increases when we add, we can move those particles. We're going to move those particles by heating them up, maybe on the burner. Okay, rubbing our hands close together. We can do that. So thermal energy is different than heat. Thermal energy is the amount of the total kinetic energy of particles in a substance. The amount of thermal energy in a substance depends on two things: the temperature. All right, so if two pots of water each have the same amount, the pot of water with the higher temperature will have more thermal energy, and the amount of substance. Okay, the more particles they are this in the substance, the given temperature, the greater thermal energy. So if you have a cup of coffee, right, and they're both temperature is 200 degrees, one's the pot and one is the cup, the thermal energy is going to be greater for the pot because there's more of it. The amount of substance is more. When there is a rise in temperatures, atoms and molecules move faster and collide. It is produced by, okay, is it electrical energy, static energy, thermal energy, or gravitational energy? Let's see if I have the answer in here. Nope, I don't. Okay, this is thermal energy. Thermal energy is the rise in temperature is because and they start to move and collide with each other, and that is thermal energy that we're adding to this. Example, orange juice in both containers is the same, but the orange juice in the pitcher has more thermal energy because they're more of a substance. So temperatures here, so let's say this is 40 degrees, right? 40 degrees, chilly, 40 degrees, comes out of the refrigerator 40 degrees. But because this is more of these, it has more thermal energy. Let's take a look at what Bill Nye says about this.
Here's a question. Which has more heat energy? This hot burning match or this beautiful ice sculpture of science? Well, the match is hot, right? The sculpture's cold. Well, they're both made of molecules, right? But which has more molecules? Well, the ice sculpture, a lot more molecules. So although they're much colder than the match, they actually have more heat energy. More molecules, more heat energy. Think of it this way. Suppose you tried to take a burning match and use it to melt the whole ice sculpture. Well, it's not going to happen, right? I mean, the match is going to run out of molecules long before the sculpture. So, more molecules, more heat energy. Ooh, ow, ow. Careful. Oh, you broke this one.
All right, checkpoint here. Would the water in a pond or the water in a full tub have more thermal energy? All right, so let me ask that question, see if I've got this in here. Even at the same temperature, the lake would have more thermal energy because it has more molecules, more and more. Okay, so here is a pond. I for some reason I put lake. More and more. Even at the same temperature, the lake would have more thermal energy because it has more molecules, right? Even if the bathtub was warmer. Heat is the energy that is transferred between objects of different temperatures. Objects at higher temperatures will transfer energy to objects at lower temperature. Heat is measured in two ways, calories or joules. Energy from the soda will transfer to the ice because it has a higher temperature, right? So here we have, and again, if you have crushed ice, it'll change the temperature quicker because it has more surface area. More surfaces of the ice, smaller pieces of ice will contact the liquid. There are more of them. All right, heat is the flow of thermal energy between two objects. Thermal energy due to interaction between molecules, the average temperature, the average kinetic energy of molecules. Nope, okay. It's the flow of thermal energy between objects. So let's take a look at this video. Turn off my pen.
When you touch an object and it feels warm or cold, what is that really telling you about the object? Here I have a metal hard drive and a book, and I'm going to ask people to compare their temperatures. Which one do you think will feel warmer, the book or the hard drive?
The temperatures.
Yeah, tell me if one is hotter or colder, or if they're the same temperature. How do they feel?
This is slightly cooler than this one.
Yeah. That's warmer. Yeah, way warmer.
Yeah, agreed.
I'd say the hard drive is a lot colder than the book. I don't know, because the book's got more knowledge.
Why do you think that is?
Metal's normally a little bit chillier if you leave it at a colder temperature.
Well, what if I said that they're both at the same temperature? What would you say?
So you're lying.
But really?
I think you're lying, yeah.
Oh, geez. Well, maybe the way I could prove it is I have an infrared thermometer. What do you think we're going to see?
I think science might be able to answer that. And I'm not a scientist.
Make a prediction for me.
I still think that's colder.
Would you bet me money?
I do it because I don't have any cash. So yeah.
Let's measure the temperature of the book.
Okay.
What do you see?
19.0.
Okay. We'll measure the temperature of that.
19.0. All right, well, now I believe you.
I'm trying to actually figure it out, trying to figure out why they would be the same temperature. They don't feel the same temperature, though.
So why does that feel colder if they're basically the same temperature?
Good one. You got the answer?
Well, I'm coming to you guys for answers.
We're creatives, not intellectuals.
Well, create an answer for me.
I'm not a scientist. Come on, you tell me.
Well, I'll try to answer that question with another little experiment. Here is an aluminium block and
Ooh, nice and cold.
a plastic block.
Yeah.
How do their temperatures compare?
Completely different. Completely different.
Aluminum's much colder.
Yeah.
Yeah?
Yeah, this actually feels colder.
Let's take this to the next level. I'm going to put an ice cube on both plates. What are we going to see?
Well, I'm guessing it would stay solid on this one and melt on this one.
So it's going to melt on the plastic but stay solid on the aluminium.
Yes, but maybe I'm wrong.
That one will melt more quickly than on the aluminium block.
You would think so. I mean, they're colder.
Yeah, because it's cold.
Let's
I
actually.
think they're going to go the same.
All right. So we put an ice cube on each of those blocks.
Wow.
What are you seeing?
Well, it is melting a lot quicker on the aluminium. I got it melting.
This is melting quicker than that one, even though this is aluminium, that's plastic.
So which one felt colder?
That
This
one.
one.
How does that make any sense?
I have no idea, you know.
Could aluminium be bad for the environment?
How would aluminium be bad for the environment?
Well, it's thawing out the ice a lot quicker, isn't it?
So you want the answer?
Yes, please, please.
It's about thermal conductivity, right? The rate at which heat is transferred from one object to another. So when you felt these blocks originally, I know this one felt a lot colder.
Yeah.
But you know from the other example we did that they must both be at the same temperature.
True.
Because they've both been outside for a
Yeah.
while. We see that the aluminium block is melting the ice faster than the plastic block because it's conducting the heat to the ice cube faster.
Okay.
With the plastic block, it's a worse thermal conductor. So heat is being transferred less quickly to this ice block, and so it's staying ice.
Okay, I believe you.
Makes sense?
Yes, definitely.
You know, in our first example, the hard drive felt colder, even though it was at the same temperature roughly as the book. And that's because the aluminium conducts heat away from your hand faster than the book conducts heat away from your hand.
Sure, that seems logical.
Which makes the hard drive feel colder,
Yeah.
and the book feel warmer. So when you touch something, you don't actually feel temperature. You feel the rate at which heat is conducted either towards or away from you. Think about this next time you hop out of the shower in winter. It's much nicer to stand on the bath mat than on the tile beside it. Not because the bath mat is warmer, but because it conducts heat less quickly away from you.
Interesting experiments. Okay, so let's take a look at this, this link here. Okay, so this is conduction. Okay, so if I take, so you can see this red block has particles that are moving very fast. So that would be considered hot. So the red block is at 100 degrees and the blue block is at 0 degrees. So there's very little movement. So we're going to see as I move these closer together, what happens to the red block. The red block cools off and the cool block is going to heat up until we get to a point where they are the same. So if you keep something in the room, the kind of the room temperature, everything in your house will get to an equal place where the hot things get cooler and the cold things get warmer until they find equilibrium. Now you can make the material smaller, like you can make the hot material very small and then touch it to the cold. Notice that the hot will cool off even faster because there's more of the cooler material. All right, how are heat and thermal energy related? When heat is added or removed from a substance, its temperature or thermal energy will be affected. Heat is not a property of a substance like thermal energy. Thermal energy is a property, and temperature are. Heat is a form of energy. So when two objects have different temperatures come in contact, energy will always be transferred. The object with the higher temperature. So I always love a hot cup of coffee. My hands are cold, right? Because that'll transfer the heat to my cold hands and makes it feel better. But the coffee is hotter than my hands are to begin with. So there are three ways to transfer heat. And one is conduction, in which thermal energy is transferred from contact. Thermal energy transfers from higher temperature to lower temperature. Conductors are material that transfer heat well, like metal. So again, we talked about that in that potassium. They were talking about metals versus insulators that are poor conductors, like styrofoam. So we don't want to have everything a conductor, because your house needs to be insulated so it doesn't lose heat quickly. You want to have clothing that sometimes are good insulators, but also when you're overheated, you want to have something that conducts or draws heat away from you so you don't overheat. Convection is a transfer of thermal energy by movement of liquids or gases. If you boil water, you'll see that water, the bubbles, move up, and then as they get closer to the top, they cool off and come back down until it's a massive bubble. So we start with bigger bubbles at the bottom, and as they go up, you'll notice that as they rate up to the top, they get smaller and smaller. And those bubbles are not air bubbles, but they are water vapor bubbles. All right, so, and it also depends on you have density as well. As you heat something up, it is less dense than if it's cool. Water density in a pond at this time of year, the more dense cool water will be at the bottom and the top water. And then that's what kind of cycles the water as we get into the summer. Cycles the water from the bottom comes up, and then and it recycles everything. Radiation is a transfer of thermal energy by electromagnetic waves. This is where you can feel the sun heating you up. Like if you ever feel the radiation through your car, you wish sometimes you had a shade, right? It's invisible. It's electromagnetic waves. Examples are visible light, infrared, microwaves, X-rays. Right. Conduction, convection, or radiation getting you sunburn. Which one do you think it is? Yes, radiation is a sunburn. Steam is convection, and melting butter on a pan is conduction. All right, there we are, ladies and gentlemen. I hope that helped you make it through your first day of state testing. If you were not there on the 31st, then maybe, and you can watch this video later. Thanks, guys.